But this one's from the 2005 free response, and it's got some stuff in it you should know how to do, so it's worth looking at. They are tracking over time the velocity of something. It doesn't even really matter what it is, but this is a time velocity graph, which you're used to seeing in physics. This first question we don't know how to answer yet, but I'm going to kind of tell you what it means. And this has been a symbol, and this is called an integral, and some people want to have on our t-shirt something like that, like we're to that for our shirt, or some sort of calculus is bringing the integral of e to the xy back, which looks like sexy back. That's been an option out there. Zimmerman had it last year in some phrase, so if we do have it, we want to change what we're saying because we don't want to look like we're copying them. But anyway, it's an integral symbol. It's like for second semester, it's our derivative. I mean, it's a really big concept, but it means the area under a curve, actually. And it reverses. You know how when I said derivative always adds the word per, it's a rate of change, right? Integral removes one. So it actually, if I remove a per from meters per second, what do I end up with? Meters, and the integration process will tell me how many meters I traveled. But mathematically, it's the area under a curve. So they're really just asking you to find the area of this trapezoid. It's a geometry problem. But we haven't covered that yet, so I'm not going to go do it. But the next one you should be able to do. This says to find the derivative 4 seconds in, which means right on there, at 4:20, you are to find the derivative, and it says at 20 seconds in, so right here. There are two answers. When you find the derivative of velocity, what are you really finding? We talked about that last chapter. The derivative of velocity is the acceleration. So, right here, you should notice what your answer is going to be. What are you going to say for the derivative of velocity at 4? Go ahead and answer me. What's the derivative right there? You should know. It is. It's undefined or it doesn't exist. Exactly. So you're going to write like this. V prime of 4 doesn't exist, or John said it's undefined. That's fine. Doesn't exist. And it says find the value or explain why it doesn't exist. We have to tell why. You can use the word there's a sharp corner, or you could say that the derivative from the left does not approach the derivative from the right. Either is fine. V prime of 4 does not exist because of sharp corner. Because of corner. Okay, and you're fine with that. If you really wanted to impress them, you'd say the limit of your derivative from the right as you approach 4 doesn't equal the limit. But that sharp corner is a problem. Right here, I can find the derivative because it's the slope of the tangent line. So really, this one's just telling me to find the slope of that line right here. So just change in y over change in x. And you can answer yours below. I don't have a whole lot of space here, so I'm going to go up here. The derivative, which is basically the acceleration I'm finding 20 seconds in, is the slope of this line right here. So I'm going to put 24, 0, and I'm going to do the slope. It's change in y over change in x. And obviously you would clean that up and reduce it. It's going to be negative because it's going downhill, so I'm not going to take time to reduce a fraction, but it's a negative. Now, the label's important. It always says indicate units of measure, which means there's a point allotted to it. How do we label change of velocity over time, which is really acceleration? We talked about every time you take the derivative, you add a word per. So it'd be meters per second. Or in physics, sometimes you write that meters per second squared. But there'd have to be a label. And I'm not going to calculate it out. That you should know. The next step, we'll wait on C also. It's not that it's hard, but the main reason for me doing this one is I want to talk about D, because this is what we covered this chapter. So in part D, it says, find the average rate of change from 8 to 20. So from 8, go do that, to 20, you're going to find the average rate of change, which your brain should immediately go, slope of secant line, correct? We'll go do that, which means my average rate of change is going to be change in y over change in x. So let's go do that. Let's write average rate of change. And if I went and find it, I'd say, well, I've got my 20 and v of 20, which you can see is 10. And then I've got my 8 and v of 8, which you can see, but I'm going to write it like that. So you would do change in y, if I was going to really write it out, over change in x, divided by, change in y over change in x. And on the bottom would be a nice 12. And again, you're going to get a negative because it's going downhill. You're going to label it meters per second squared. I'm not going to finish the arithmetic. You should understand that problem. This is the reason I'm doing this one, though, because we just covered mean value theorem. Does the mean value theorem guarantee a value of c in that open interval so that the instantaneous rate of change of whatever it is, the car, is equal to the average rate of change? It's tempting to say yes. Right there. Carrie, can you tell me why the answer is actually no? Do you remember the hypothesis for the mean value theorem? What had to happen? What, continuous, which this one passes, and differentiable, exactly. And this isn't differentiable where? At 16, exactly. So you would say no, and then if it said why not, you would say not differentiable on the entire open interval, but specifically it's not differentiable at 16 seconds. Now, physics-wise, we're finding the acceleration, so there's a constant acceleration here, and then it goes like that. And I was kind of asking Miss Anderson, I said, well, what does that mean in a physical model? Because I'm a calculus teacher, not a physics teacher. I said, does that jive with us saying, you know what, I can't calculate the acceleration there? And she said, yes. She said, something's going constant, and then there's an abrupt change. And she said, unless you can really hone in there and get some curvature, you can't have that happening. It's kind of like I don't know how, like you just jump from one to the next, and you can't, does that make sense in physics class? But for us, we can't use that. We just have to say it's not differentiable right there. So again, I wanted you to see where some of this stuff ties in AP-wise. Now we're just going to go finish 3.3. So I want you to go into your notes to right, not there, here. We're going to talk about some of these questions. So I've got a graph up here of a continuous function for sure. First of all, we're just going to talk about finding some values on here, just so you got the gist of what you're finding. When it says, again, find f of negative 3, I just want the y value at negative 3. So that would be 2. Piece of cake. When it says to find f prime at 2, it means I want the slope of the tangent line at 2. So since that one's a horizontal tangent, it'd be 0. When it says find f of 4, that exists. The value of the function at 4 is 4. So you would say 4. But the next one up, when it says what's the derivative at 4, you'd say it doesn't exist because of that cusp up there. All right? So know how to answer these questions. When it says to estimate the second derivative at 0, this is a good question because right here, if I were to estimate the second derivative, the first derivative, if I were to graph it, this would be decreasing, 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 and then it'd be the most negative it could be, and then still be negative. So there'd be something going like this here. Do you agree with me? It's its most negative, like if this were a roller coaster, this is where you're most negative, right? So it's going to bottom out there. So my second derivative would be my derivative of this one. What's the slope right here? 0. See what? So kind of know what they're asking you for. This is what's the y value, what's the slope of the tangent line. This is what's the slope of the derivative graph. So let's answer a couple more questions. Where is the function increasing? Well, obviously that's kind of where you're going uphill. Mathematically, that's where our slopes are positive. So you'd say on negative infinity to negative 2, I'm heading up. My slopes are positive. My slopes are also positive from 2 to 4, and those are open intervals. At 4, I've got a problem. Where is it decreasing? Obviously where it's going downhill. So from negative 2 to 2, I'm heading down. I'm also heading down from 4 to infinity. And again, you're just looking for where those slopes are positive, where they're negative. I'm going to skip the sketch of f prime because we're going to talk about that later. When it says, where do you have critical values? I would tell you again, it's where the slope is 0. So right there at -2 is considered a critical value. Another critical value at 2. Third critical value where? 4, exactly, because it's not differentiable. So you have 3 critical values. Those are what go under consideration when I'm looking for my relative extrema, right? All right, so let's go down here. Then it says, where is it not differentiable? We already said when x is equal to 4, we've got that corner or that cusp there. All right, and I think the rest of this you guys get. We were good at it. So I'm going to move on to the next page. We're almost done. So today we're going to do more of a graphical approach. We already talked yesterday about the math, where you need to find the critical points. You need to find where a function doesn't exist, and then you use those to determine whether it's increasing or decreasing. We're going to do a little more graphical approach on this one. I'm going to have you draw a big bold line right here, because these are 2 completely separate problems. So go draw this. Right here, from here on out, you're going to have to watch really carefully whether they're graphing f, f prime, or f double prime. This is the function's graph right here. There's some in your homework, though, where they're going to give you the graph of f prime and ask you to analyze it. But you should be really comfortable by now sketching, right? Let's go take a look at it. Right here, my derivative is very negative, very negative, very negative, very negative, very negative, very negative, less negative, 0. So I've told you to put dots on there. But now just stop for 1 second. On the derivative graph, the x-intercepts are really going to represent what part of the original graph? The what? The extrema. Yeah, the relative maxes and mins. So that's going to be important to note that if you're given the graph of f prime, every time it hits an x-axis, it means the derivative was 0. So you had a peak or a valley. So that's going to be important reading it backwards. Reading it forwards, we need to be below the x-axis because these are negative. So we start from below, we hit this, we are above the x-axis and the most above right here. This is where it's the most steep. So you kind of peak out there, you come back down. So again, right here represents where my graph was increasing. Do you see that? Because it's all positive slopes. It's less positive right here, but it's still increasing. Right here where my graph is decreasing, I have to be negative for my slopes. I'd be my most negative right there. So it'd be something like that. But I want you to stop and kind of analyze the important parts of this. We've got, when you're increasing, I want you to write this, okay? When you're increasing, your derivative graph is above the x-axis. When you're decreasing, likewise, I'm going to save some time here, your graph is below the x-axis. So you should be good also reading them backwards. So let's go down here. I'm talking fast because I have 2 minutes. It says use the graph of f prime to identify where the function was increasing. So this is the graph of f prime. This is graphing the derivatives, which means the derivatives are positive here, the derivative is positive here, and in this whole chunk over here, the derivatives were negative. You see what I mean? So when you're using the derivative graph to find where it was increasing, it would be increasing from negative infinity to -3, because I'm above the x-axis. Where are my relative extrema of the original graph? At -3 and at 1. Okay, so it's also increasing from 1 to 3. I'm going to stop for a second. Obviously, it's decreasing between the 2. But if they asked you if this was a relative min or a relative max, right? If the slopes went from positive to negative, max or min? Max. So actually, the point -3 is a max. Actually, it's a relative max, so you should put that on there. -3, whatever. Same over here. 1, it goes from negative to positive, so the original function went like this, right? Basically, you're looking at a cubic function is what it originally was. Its max was here, its min was at 1. All right, homework-wise, just so I can stop there, I'm going to keep going, but for the video, you're going to take out on the homework, you're only going to go through 69 odd. So it's going to say through, this is for people listening to the video, it's going to say to go through 79, only go through 69 odd. Otherwise, do the rest of it, and that's it for them.